Okay, so before we go any further, I just want to define some terms here because there are certain words that scientists use that we use in a slightly different context than you're used to in everyday life. And in particular, hypothesis, model, and theory. And so I want to make sure that we're on the same page here using the same definitions for these terms. So a hypothesis is what you would call an educated guess. It's a possible explanation for something based on what you currently know. So you observe a phenomenon, you come up with an idea about what could be causing that phenomenon. That's your hypothesis. A model, we're going to go into a lot more detail about what a model is, but basically just a simplified version of something. It's a simplified version of the world around us used to explain and make predictions. So for example, you hear about a weather model. We'll build a simplified version of what's happening in Earth's atmosphere to predict what the weather is going to be tomorrow, the day after that. Usually these models are very mathematical in nature, a lot of math behind them in order to describe physical phenomenon. And finally, theory. And theory is the one that has the biggest difference to how we use it in sort of colloquial speech. So a scientific theory is a model that has been repeatedly tested and has constantly survived these tests. So you can come up with any hypothesis you want. You can build that into any sort of model you want. But then you have to test it against observations. You need to come up with observational tests that would show if that model is correct or not. And a model that continually survives, that continually makes accurate predictions, you constantly try to disprove that model and you fail every time because it always makes accurate predictions, that model can be promoted to theory. And so, a hypothesis is an educated guess. A theory is a hypothesis or model that has survived constant attempts to disprove it using observations. And so you hear terms like the theory of gravity or the theory of relativity. These are, really, really good models that describe the world around us that we have tried and failed to disprove via observations. And so again, a theory is a very, very solid model or very, very solid hypothesis that has survived repeated tests. And an important point here, you can never prove a theory beyond all doubt. All you can say is that every single test we've tried, it has survived. We've thought of everything we could to disprove this model, but we failed. We could not think of it. We could not perform a test that disproved this model. It passed every test we thought of. And again, that's only up until now. Maybe you'll think of a better test tomorrow that will disprove this model, but everything you've tried up to this point has not disproved this model, and therefore this theory continues to survive. So again, there's always the possibility for a theory to be thrown by the wayside, but theories that have survived repeated tests are less and less likely to be disproven. Although you can never really prove beyond a reasonable doubt that a theory is correct. And we'll come back to these terms and the scientific method a couple lectures from now. Okay, so a little bit more on models. So models, the way you're probably used to hearing this word is something like a model ship. And a scientific model is a lot like that. It's a simplified version of a bigger thing. So this model ship here is a simplified, smaller version of a full life-size ship. It has, some features in common, the sails, the riggings. This model may or may not actually be seaworthy, but it at least has things that represents parts of the full-size ship is trying to represent. And again, you can imagine a very, very simplified model. You can imagine building this out of fewer parts, or you could imagine a much more complicated model. You could try to reproduce every single part on the actual ship down to the people and put that in your model as well. And so in this analogy, again, you have a choice about how simple or how complicated you want the model to be, how carefully you want it to reproduce real life. And that's the same for scientific models as well. We can have very simplified models of how the world works, or we can add more complexity, more features into our models, make them more complex, add more mathematics to them to try to better fit the observations. And in general, this will be the typical rule that a simplified model will mostly fit the observations, but not perfectly. But as you add more complexity, as you better account for the things that are in real life, the better your model will fit these observations. So I'm just going to give one example of what we mean by model. And so I'm going to ask you to imagine this hypothetical. Imagine you have a friend who tomorrow is traveling from New York to Los Angeles. And what you want is a model to figure out where in the United States your friend is as a function of time. Where will he be 3 hours after he sets out? Where will he be 12 hours after he sets out? Where will he be 2 days after he sets out? Where in the US will he be? And so you can start with a hypothesis. And how about a hypothesis where your friend is driving across the country and is going to travel at a steady pace? If you do that, you can look up the formula you need. It comes out to be the distance from New York is the average velocity your friend is traveling times the elapsed time. And you can, go to Google Maps and figure out, that there's about 2,400 miles between New York and Los Angeles. And the typical drive takes about 4 days. And so you just have to plug these numbers in. And you get basically a mathematical model. You plug in the amount of time that has elapsed since your friend started, and this is the estimate for where he will be in terms of distance from New York. Okay, now right away you probably saw that this was an incomplete model. Your friend probably is not going to drive for 4 days straight without rest. Your friend will probably find a nice hotel somewhere and sleep for the night and then start again in the morning. We don't have to throw away the model completely. We just have to basically refine it. We have to make a few corrections, add some more complications, and the model will still do what we want it to do. And so rather than what we did before, which was looking at the number of miles over the total number of days, we can assume that our friend is only going to travel for about 10 hours during the day. We make our equation a little bit more complicated. You don't have to worry too much about the details here, but essentially we assume our friend is only traveling during daylight hours. We assume he travels 10 hours a day. And now we have a more accurate model of where he is. He'll move from New York. He'll stop for the night. He'll move a little bit further. He'll stop for the night. And we have a more accurate model of where our friend will be. And it'll have a lot more accuracy, more precision than the previous model where we assume he travels at a steady rate, whether it's nighttime or daytime. Okay, and again, you can keep adding complexity to a model. So in this toy model, instead of just drawing a line along the globe, I can look at actual roads. I can figure out what road I think my friend is likely to take. I can look at speed limits. We're going to assume our friend obeys the law and stays below the speed limit on any road he takes. And we can figure out a much more accurate model than, again, assuming that he travels at a uniform pace so long as he's moving. Even road conditions, is he traveling during rush hour? Is there construction happening that will slow him down? What sort of restaurants does our friend like? Where is he going to stop to eat? You can keep throwing these extra details in the model. The model gets more and more complicated. It's no longer one equation. There's going to be lots and lots of equations. But again, the more complications we add, the better we'll do at predicting where our friend is going to be as a function of time. Okay, but maybe our model is fundamentally wrong. We went into this with the hypothesis that our friend is driving. What if we learn that our friend is taking an airplane? Well, we don't have to throw away the model completely. We just have to change our terms a little bit here. So again, we can use this equation. The distance from New York is the average velocity times the elapsed time. But we don't have to, we're not going to use the velocity in a car. We're going to use the velocity of an airplane. And so again, it's about 2,400 miles, but it'll only take an airplane about 6 hours to make that journey instead of 4 days. So again, the underlying model was fine. We just had to refine the terms we're putting into there. But there are going to be examples where the model has to be thrown away completely. If we learn our friend is taking a boat, if he's taking a boat from New York to Los Angeles, our model is not going to help us. Our model assumed he was traveling across the United States, the land of the United States. If our friend is taking a boat, then we need a completely different model to explain where our friend is as a function of time. And stepping back to the analogy now, we would call that a scientific revolution or a paradigm shift. The discovery that our model is so fundamentally flawed, we need a completely different model, completely different hypothesis to explain the observations. The one we've been using before just did not work. And for the rest of the lecture today, I'll talk about setting up one such example. And then in the next lecture, we'll talk about the scientific revolution or paradigm shift that was required to overthrow it.